Hello, my fellow Almontians, and welcome back to Broadcast from the Bunker. Today's lesson is going to be a wrap-up of all the different rock types and minerals. You worked on a review sheet, hopefully, yesterday, and we'll get to that in a minute. All right, we'll start out with the do now. 13 to 16 in your GC. Work hard on them, and I'll meet you back here in a minute. All right, let's see how we did. Please take note. Homework assignment tonight in the textbook, page 130 to 136. Looking for 15 bullets. It's a little metamorphic reading there. Okay? All right, let's get started. Okay. Do now questions today, dealing mostly with this diagram here for questions 13 to 15, and then 16 is separate. So there it is, number 13. The latitude of position G is 23.5 south, during which months would the sun's vertical ray, that's the direct ray, be moving northward between locations G and E. So we got to go to the diagram. We're looking for points G and E. We're heading north. And what months would that be happening? All right, so here's the diagram. Here's point G. Here's E. It wants to know when we're going to be moving north from G to E. Well, the sun's directly overhead the Tropic of Capricorn. That's what G is, on December 21st. So if this is December 21st, as we go north, it would be January, February, March, April, May, June, July, August, September, October, November, December. So December, January, February, we're heading toward the north. That's got to be your best answer there. All right, for number 14, at which two locations could the sun be directly overhead at local noon or solar noon sometime in the same 24-hour period? So during the same day, which 2 points would have the sun directly overhead at the zenith? It's got to be 2 places at the same latitude, right? If you're at different latitudes, that wouldn't happen. So you're looking for 2 points that are at the same latitude that could also get direct sunlight. Well, if you go back to your chart here, the only 2 possible points at the same, well, 3 possible points at the same latitude are D, E, and F. They're all on the equator, so they could get direct sunlight at some point of the year. So you're looking for an answer with either D, E, or F. All the other ones are at different latitudes. So there it is, choice C, right? D and F. 15, when it's noon at location E, what time of day will it be at location D? All right, so it's noon at E. What time at D? So it's noon at E right here. What time at D? Well, remember the Earth rotates counterclockwise, so this is later in the day, right? This would be, if this is noon, this would be like 1, 2, 3, 4 p.m. But it wants to know about position D, so that's earlier in the day, so that would be like 11 a.m., 10 a.m., 9 a.m., the morning time. So if you look at your options, that should be one of them. And there it is, morning time. Finally, 16 here. Which diagram below best represents the illumination of the Earth on the first day of summer, right? AKA summer solstice in the northern hemisphere. So you got to find an Earth that's tilted towards the sun and the entire Arctic Circle is lit up. So that's cut in half. That would be an equinox day. This one, the north, the Arctic Circle is completely darkness. That would be your winter time. This is looking for summertime. So A and B are out. Here you go. There's the Arctic Circle completely lit up, tilted toward the sun. That looks like our best answer. And here, once again, we're split in half. That's an equinox day. So you got to go with choice C because the North Pole is tilted toward the sun there. All right. Any questions on those? You can sort of leave them in the comments. You can do remind. It's up to you. But again, if you leave them in the comments down below on the video here, everybody will be able to see your questions, see my response, and I think it would help everybody out. All right, let's move into our rock review that you guys worked on diligently last evening. Okay. And once again, don't forget your homework tonight, folks. Bunch of beautiful gemstones down there. Right, we talked about minerals not too long ago. Outside looks just like an ugly rock, but you never know what's on the inside. Right? Take time and, well, you've heard the expression, stop and smell the roses. Well, stop and crack open a rock. All right, so here we go. Quick little video for you. It goes through basic rock cycle. Check it out.
Rocks are classified by how they are formed. They fall into one of three categories. Igneous rocks are formed from the solidification of magma rising out of the mantle of the Earth. When magma flows onto Earth's surface, becoming lava, it cools very rapidly. This allows little time for crystal growth, and the rock is fine-grained. This type of igneous rock is called volcanic or extrusive. Basalt is the most common extrusive rock. The lava flowing from Hawaiian volcanoes is basalt, and basalt covers much of the ocean floor. When semi-molten material becomes trapped in pockets before it reaches the surface, it cools very slowly. As it cools, the atoms that make up the magma bond in a regular pattern, creating crystals. The slowness of the process allows the crystals to grow quite large. These are called intrusive or plutonic igneous rocks. Granite is created in this way. Sedimentary rocks are formed by the weathering and erosion of pre-existing rocks on the Earth's surface, the remains of once living organisms, or a combination of both. As older rocks are broken apart or dissolved by water, the particles are blown away or washed downstream, where they settle on plains or the bottom of lakes. With the passage of time, more and more particles accumulate until the sediment becomes deep and thick. Pressure at the bottom becomes so great, the sediment fuses together and becomes rock. There are many types of sedimentary rock. Two of the most common are shale, made from what was once mud, and sandstone, made from sand. The Grand Canyon dramatically shows the layers of sedimentary rock laid down over millions of years. Metamorphic rocks are formed when existing rocks are altered by heat and pressure. Recrystallization and chemical changes in the rocks occur, so they are transformed into rocks with a different structure. The parent rock, from which the metamorphic rock is formed, can be either igneous, sedimentary, or another metamorphic rock. The most common way metamorphic rocks are formed begins when a rock becomes buried under other rocks. This can happen when rocks are pulled back into Earth's interior through the movement of tectonic plates, or as rocks and other materials cover the parent rocks, gradually increasing the heat and pressure. When temperatures rise over 200 degrees Celsius, the crystalline structures of the materials in the rock are broken down and transformed into new structures. Metamorphism can be instantaneous, such as when rocks are sheared at plate boundaries, or it can take millions of years. It may seem that rocks are eternal, but they are constantly subjected to the changing conditions around them.
All right. So last night, like I said, you guys worked on the stations sheet here. Hopefully you were able to complete each station in 5 minutes or less. If not, you need to study more. Hopefully you read all the instructions, you used the materials I gave you in the GC to help out. You should have completed the entire worksheet and submitted it last night for credit. If not, pause the video and complete it now for partial credit and stop being lazy. All right, let's get rolling here. Station 1, it says on the grid on your worksheet, construct a bar graph to represent the hardness of these minerals. Here is the mineral chart from the reference tables. The minerals you had to look for were fluorite, halite, quartz, and galena. So go to your chart here. Fluorite is a 4. Halite is a 2.5. Quartz is a 7. And galena is a 2.5. So you had to put those in order on your chart. And it should have looked something like this. All right, so moving on, the next part there, it said, number 2, the bonus question, identify the mineral that has the atoms or elements arranged as shown in the basic structural unit. Well, this structural unit here is that pyramid thing we had in the front of the classroom, right? They call it a silicon-oxygen tetrahedron. And that, of course, is in quartz. If you go back to your chart here, you go to quartz, there's your silicon-oxygen molecule there, and it makes that tetrahedron shape. And that's what that's talking about. Quartz, silicon, oxygen, tetrahedron. Okay? Okay. Then we get to station 2. Let's see. The first question said, state one igneous rock that could be placed in the flow chart at D. Well, D is down here. So follow your flow. It says lava, right? Not magma. So lava, which means it must have cooled quickly. It exited the earth. You go down, it's an extrusive rock. It says glassy. What could it be? Well, here's your igneous chart. Extrusives are up top. Glassy is here, right? So it could have been either obsidian or basaltic glass. So I chose obsidian. You could have put basaltic glass as well. All right. The next one, what does it ask you here? Give the numerical grain size range that should be placed in the flow chart at C. Well, C is over here. So now we're on the other side. We got magma, that's intrusive. It must have cooled slowly. It's a coarse texture. What grain size would it be? We'll go back to your igneous chart. Coarse textures are here and the grain size right there. So 1 to 10. Hopefully you had that down there. And there it is, 1 to 10. All right, the third one, it says identify the cooling rates. Well, if you're intrusive, you're going to cool extremely slowly. You're going to get big crystals. If you're extrusive, you're going to cool much faster. So your 2 rates, right, slow and fast. And hopefully you figured that out last evening. Okay, moving on to station 3. It asks you first to base your answer to the drawings of 6 sedimentary rocks labeled A through F. There they are. Classify the sedimentary rocks by their texture, placing them in the correct table. So remember, the textures have to do with the size of the grains. So when you looked at these rocks here, A, B, C, and D were all clastic rocks, right? If you look at their names, they're all clastics. So that would be the texture clastic. So hopefully you put those 4 there. Okay. And then the next box, well, if you see the fossils, if you look carefully, that's living things biology, so that would have been bioclastic in E. And, of course, odd man out there, rock salt, you know, is a bunch of crystals, that would have gone in F as a crystalline texture. And you can double check that on your chart here, right? Crystalline rock salt and limestone can be bioclastic right there. Okay. Bonus question, identify the two rocks that are composed primarily of pebbles and cobbles. You can probably tell by the pictures alone, but if you go back to the tables, pebbles and cobbles right here, you're looking at conglomerate and breccia. Okay, and that's highlighted right there. All right, moving on to station 4. This is going deep within the earth. The deeper you go, the hotter it gets, the more pressure there is. First question was in the diagram, identify the types of metamorphic rock found when clay materials are buried to a depth of 14 kilometers and explain. Well, go down to 14 kilometers. Right, here's clay, but go down to 14, scoot over to the line, and you get phyllite. Okay, and there it is, right? It was clay at the surface, but heat and pressure turned it into slate, and even more heat and pressure turned it into phyllite. Then it says explain why, number 2, why gneiss would not form at a depth of 27 kilometers and 800 degrees. Well, 27 kilometers is all the way down here. 800 degrees is all the way over here. That's degrees C, by the way. And what would happen to gneiss? Well, at that point, it would melt. Okay, so you're not going to make gneiss. It would simply melt back to magma, and the rock cycle would start over. All right. Jumping down to station 5, it says complete the chart by writing the missing terms in the spaces labeled A, B, C, D, E, and F. So we got to figure all these out. Well, we got sedimentary, igneous, and the third rock type would be, hopefully you guessed it, metamorphic. B, if you're not intrusive, you are, well, extrusive. C, where is C? Oh, down here. So a sedimentary, a land-derived sedimentary rock. Could have been a bunch of them on that chart. If you go back to the chart, land-derived. Actually, let me go the other way. Could have been sandstone. Oh, my clicker's going crazy. Conglomerate, shale, but I put shale down here. All right, E is next. Sedimentary rock is either land-derived, chemical, or it's got that fossil, right, that bioclastic nature, which would make it organic. And then F here, if you're igneous and you're intrusive, well, what rock could you pick? Well, obsidian is extrusive and intrusive rock. You could have picked either granite, pegmatite, gabbro. I put down a granite. Okay. All right, then you got the station 6. Here you had to figure out the specific name, not just the family, not just igneous sedimentary, but a specific name of the rock, A, B, or C. Well, A, it says compaction and cementation, so hopefully you're thinking sedimentary. But it says fragments that are less than 0.0004, so go to the chart, grain size, less than 0.0004, slide over, and you're looking at a shale. Okay? So A would be a shale. B, it says high-grade metamorphism, so of course that's metamorphic. And then it says banding is present. So go to your metamorphic chart. Banding, a high-grade metamorphism, that would be your gneiss. Okay? So we have shale, we have gneiss, and the last one here, it says felsic magma, slow cooling underground. So we're felsic, we're on the light side of the chart, the left side. Slow cooling, so you got big crystals. What's a light-colored igneous rock with big crystals? Well, go back to your chart here, felsic side, big crystals. You could have picked either granite or pegmatite. Okay, so hopefully your chart looks something like that. All right. Before you're allowed to click out of here, we got a quick little exit card. According to the reference tables, identify the minerals composed in a quartzite. So go to your charts. What kind of rock is quartzite? Well, it's a metamorphic rock. So if you go to the metamorphic chart here, quartzite's on the bottom, and it comes from, of course, a quartz sandstone. All right. It wants to know the minerals in quartzite. Well, that would be mostly quartz. Number 2 there, it says identify the rock. Stop making fun of my handwriting. Identify the rock that is extrusive. So we're talking igneous now, right? Extrusive, that's volcanic. Felsic and has a glassy texture. So we got to go to the igneous tables. Extrusive, felsic. So extrusive is up top. Felsic is to the left. Glassy puts you with an obsidian right there. Okay. Last two here. Finish strong, folks. Name the rock that has a classic texture. Well, you're talking classic, that's sedimentary. And a grain size of this range, 0.006 to 0.004. So let's go back to the sedimentary chart, 0.006 to 0.004. Well, there it is. That's silt. Put it together and you make a silt stone. I'm trying to write on a vertical screen, so it's coming out a little sloppy. And last but not least, identify the minerals. So now we're at the mineral chart that is non-metallic, has cleavage, and a hardness of 3.5, reacts to acid. So go to your mineral chart. Non-metallic puts you towards the bottom. A 3.5 is here. Cleavage is the check on the left side, and then go over. It says bubbles with acid, and sure enough, there it is. That's your dolomite.
I'm just worrying about it.
Okay. All right. So hopefully you did okay on that. I certainly will check your results when you submitted that on the GC there. And you said, but Mr. Reinhardt, how can I ask you other questions? Remember, folks, the best way is probably to simply type in the YouTube comment section below. I'll write you right back. Or if you want to do it privately, you can send your question to Remind. And if you're not in Remind at this point, there's your code right there. All right? You guys have a great rest of your day, and I'll catch you next time at Broadcasts from the Bunker.